Okay, great. Thank you so much for inviting me. So today I will talk about a work that is actually presented. Oh, sorry, let me find the right spot. Okay, let's hope this is good. I will present to you a crossover. It is a highlight work with Cheyenne, my student who is sitting there. And it is about cross-modal 3D scene representation and alignment in a feature space. So starting, for those that do not know the difference between multimodal and unimodal models, a unimodal model takes only one modality, let's say only images, and makes some kind of output out of it. But when we're talking about multimodal models, they will use a combination of different modalities in order to make a certain output. And the good part about having a multimodal model is that you can actually enable knowledge transfer and experience transfer across different modalities. And of course, there have been many works that work on multimodality, such as, particularly in the 2D world, lately we have a lot that have great results, such as Clip or DALI, but most of the works do focus on connecting images with text. ImageBind is a very interesting work in the 2D domain because it's actually able to connect many different types of modalities, such as audio, images, echocentric videos, thermal data, text, etc., in order to create one unified embedding space. And the interesting part on which we also get inspired is the fact that it doesn't need to have all data aligned together for all modalities. And I will explain in a second what that means. So in the 3D space, there has also been some multimodal models. However, the majority of them, if not all of them, are just for the object level. So they are able to create multimodal interactions for single objects. For example, there's ULIP2 or PointBind that use a combination of point clouds, images, and text. PointBind also does audio in order to create that unified embedding space. However, these works actually require this perfect modality alignment and need complete object data. And what do I mean by that? It needs, first of all, to have every data point, like every object that you're going to give to it as an input during training, you need to have it in all possible modalities that you're using. So you need to have it in a point cloud, you need to have it in an image, you need to have it in a text, you need to have it in an audio, anything you are working with. Also, you need to have it more complete. So essentially, they're working mainly with synthetic data, and they don't have noisy potential 3D reconstructions in order to be able to perform the inference and training as well. It also doesn't have a context of a scene, an object within a scene, within the context of a scene. That is because they only look at single objects and not how they are actually placed within the scene. And what we do want to create is to go beyond object and multimodal understanding to scene multimodal understanding. And finally, of course, there are certain works that, particularly in the visual localization domain, that do have more multimodal understanding with the use of 3D scene graphs. However, they do require a lot of semantic annotations in order to work. So with our work, Crossover, we're trying to address all of these three limitations. And we're going for a more flexible alignment of 3D scenes. And when I talk about alignment, clarifications, I always mean about the 3D feature space. Sorry, the feature space, not 3D, any feature space, embedding space. We tackle 5 different modalities that have to do with scenes, images of scenes, point clouds of scenes, CAD models of scenes and objects in the scenes, text information about scenes, and 2D floor plans of scenes. And in contrast to prior work that, as I said, needs all the modalities together in order to perform training, so you would need the point cloud of the scene and the CAD model and the 2D floor plan, the text and the image, we are actually removing that dependency, and we are only requiring pairs of modalities. Again, similar a bit to what ImageBind was doing. In our case, we only use one modality as the main modality that we're going to align everything else with, and that is the image space. Our choice is obvious for 2 reasons. The first one is because there are way more images that we have to represent our world than anything else. And also because of that, we also have more good pre-trained encoders in that field. So we use that to align every other modality with. Which means that during training, we would only need a point cloud and an image pair, and we don't need the same data point in the text format. And that, as you will see in our experiments, allowed to create some emergent behavior across modalities that have never been seen together during training. So we are actually able to create an alignment in the embedding space also across point clouds and CAD models or any other modality combination. And crossover has 3 steps. One of them actually starts with an instance level alignment. So we do look initially about objects in the scene. And that is because individual objects like ULIP does or PointBind does, because we have a lot of encoders, pre-trained encoders that we can leverage in order to make sure we get a good initial presentation of what geometry looks like, of what our objects could look like within the context of a scene, as I will explain in a bit. And then we are able to actually, in the next 2 steps, focus more on the scene level alignment to really see how they are all configured together to create the context. And here is how crossover looks like. So given an initial scene and certain object instances within it, you see here object 1, 2, 3, etc. We are gonna start by doing the instance level alignment. As I said, we work with 5 modalities. However, we don't look at 2D floor plans on the object level. So we're only gonna deal for now with 4 modalities: the text, the images, the point cloud, and a CAD model of that object. The point clouds are actually derived out of the reconstruction of the space, so they are not perfect point clouds that were sampled on synthetic data. For the text is actually a more spatial related text. So it describes where this object is with respect to other objects within the scene. So it's more of a referral text. As you see here for the sofa, facing the recycling bin, the couch is to the right of the bed, the couch is in front of the table. So this is more about relationships with other objects. And that already starts putting some context within even the instance level alignment. In terms of images, we are actually using multi-view images, and we have found that about 10 images actually gives us a very good performance at the end, and those are sampled from within the scene in the same way as SceneGraph does. And so we have these 4 different modalities for our objects instances, and we're going to train a 1D and 2D and a 3D encoder for each dimensionality, meaning that the 1D encoder will take the text, the 2D encoder will take the images, and the 3D encoder will take both point cloud and mesh and CAD models. And I'm going to use a contrastive loss in order to create an embedding space that puts everything together in a unified feature space. Now, as I said, we want to leverage pre-trained encoders, right? So the way we do it is for the 1D encoder, we're going to use initially a blip encoder to get that knowledge extracted from. For the 2D space, we are using DynoV2. And for the 3D encoder, we are using the image to point cloud mask contour encoder. And that also for the CAD model as well. And we add some layers, shallow MLPs at the end of each of those encoders. That is what we're actually training out of this network. Okay, so given this information that we have here, and we created that embedding space, we're going to go into the second training of this, which is about the scene level multimodal interaction. And here what we do is we get all the features that we have from the instance embedding. So we see here for object 1, we might have all modalities available, but for object 3, we only have 2 of the 3 modalities, let's say, or 2 out of the 4 or whatever. And we're going to take all these and we're going to do, first of all, pooling based on each modality for all object instances, which means, for example, for this yellow modality, we would do an average pooling over all the object instance features that we have. And then for this modality as well, and for this modality as well. And that's how the first step works. And then we will do a multimodal fusion that takes all the 4 modalities that we have and combines them together into the one embedding space and aligns them very well. Now, we could stop here. If we stopped here, we could actually have a very nice unified embedding space, at least for the 4 of the modalities that I have discussed. However, how it would work is that you would need initially the instance segmentation to have in ahead of time. And you could do, if you had that instance segmentation, you could take your scene, you would pass all the instances from any of those encoders for which you have data. So maybe some instances are in point clouds and some other instances are in images and others could be in text. and then you would pass it through the encoders, and you would get these final feature vectors, and you could do retrieval, for example. However, that means that we do need semantic segmentation. And we all know how difficult that can be, particularly to generalize into the real world and any kind of scenario. So we thought, how can we remove that? Spilling the beans. Good. How to remove the dependency on the semantic information. Okay, so let's see how we do it. For the scene level, now we're going to do a third training. It is the last one. And we're going to take multi-view images from the entire scene, which we sample from camera trajectories that have reconstructed the scene. Then we're going to also have to do floor plans during our training, because we do want to add that modality as well, now in the scene level. We have referral texts that tell us more about all the objects in the scene. And then we're going to use all these in order to train another 1D encoder, another 2D encoder, another 3D encoder, which we call the unified dimensionality encoders. And I will explain what is happening here. So what we are giving into these encoders is just the entire scene data. So for the 1D encoder, all the referral text that has to do with the scene. For the 2D encoder, could be all the multi-view images of the scene, or it could be a floor plan of the scene. We do not differentiate in terms of what an image means, because our floor plan is a rasterized floor plan. And then for the 3D encoder, we're going to use the point cloud of the scene. And we're going to train these encoders specifically to try to bring them as close as possible to this multimodal fusion feature space that we created before, which is the FS. Right? So before, we were able to create a very good embedding space with 4 different modalities, but required instance information. Here, what we want to do is we're not going to give instance information as input as we did here. We're just going to give you the raw scene data. And we want you to be able, given this information, to bring it as close as possible as you would do if you had the instances at hand. And once we train these 1D, 2D, and 3D encoders, we are able to perform different tasks. And the one we mainly evaluate on is the retrieval task, right? To see how good is our representation. So how can we do cross-modal scene retrieval during inference? It's very simple. Given a database, let's say, or floor plans, let's choose that modality, and a query scene point cloud, we're gonna pass the query point cloud through our unified dimensionality 3D encoder, and then the floor plans for the corresponding 2D encoder, and then we're gonna just see which one, based on similarity, which feature vector is the one that corresponds the best. And that is how we can find the closest floor plan of the point cloud in the database. We perform different experiments, and we have a lot in the paper, big tables with big numbers, but I'm going to try to show some of them here and make it as simple as possible. So first of all, we're going to look at object instance matching. What does that tell us? Given an object in the scene, can you find any other object? So can you find its corresponding object in another modality? So it's the cross-modal instance matching. Here's a spider plot of our performance. This is on Scanet. What you see here in this plot is how well we perform with respect to pairs of modalities. So image with text, this has been specifically trained on. Image to CAD model, also specifically trained on. Image to point cloud, also specifically trained on. But we also evaluate on this emergent behavior that I described before. So a point cloud to a CAD model, this has not been trained for. A point cloud to a text, or a CAD model to a text. Now, we also compare with baselines. Ours is the green, the one that you see on the outer side of the spider plot, because yes, we perform the best across all these methods. Then we evaluate against our instance baseline. So when we do require the semantic information to be given, we also compare against the point bind and ULIP and see which one performs the best. And as you see, point bind and ULIP do quite well on image to text, but they have a bit of a struggle with respect to the other modalities. They also do quite well, particularly point bind on CAD model to text. That is because they do use synthetic data. So they don't really do point clouds, they do CAD models as their point cloud. But see how our emergent behavior modality is actually very close to the actual training modality for the other pairwise training that we did. We also evaluate on cross-modal sim retrieval. And we compare the recall with respect to different pairwise modalities. And then we have, again, image and point cloud, image and text, as well as point cloud to text. And we see here, again, the different kind of baselines that we have, including ours. The coloring is the same. So green is ours. And what we see is what happens in the top 1, top 5, top 10, or top 20 retrieved scenes. And we see how our method performs the best in all of the cases across all of the experiments. And we do not rely on having semantic information as an input, which is great. And we, as I said, outperform prior work in all pairwise cases. Now, we also perform experiments with 3R scan dataset. For those of you who don't know, the 3R scan dataset is based on temporal information, which means that since change over time. But we have these experiments in the paper because it would be too many results to show you with too many numbers. But what I have here is certain questions that we ask ourselves to see, are we really creating a good embedding space for these cross-modal interactions for scenes? And so we thought, well, you know, in ScanNet, we actually do have all modalities available for each data point. So what if we did a training that is what, let's say, ULIP or ULIP2 or point bind do, where for each data point, we're going to train on images, point cloud, CAD, text as well. Can we actually do better than if we align everything only with one modality, which is the image for us? What we saw is that, you know, what you see here in the table, you see with gray the different pairwise modalities we evaluated on. I is always image, P is point cloud, R is text, M is CAD model, etc. These are the 3 down here are the emergent modality behaviors that would happen with ours. Ours is the more flexible alignment with the image. All pairs means we trained on all pairs. And here you see the sim level recall on 25, 50, and 70%. Now, what you see bold is, of course, best values. And if you just take a quick look at this table, you will see that ours almost always outperforms trained on all modalities that exist, or performs extremely close. What does that tell us? That tells us that actually it is very powerful to perform this flexible alignment, and it's not always good to be able to train on all data points together. So we may want to consider going forward to do this more flexible pairwise modality training. We also thought, well, all the experiments we run to evaluate, particularly on the ScanNet dataset, were around whether the point clouds and the CAD models, for example, were of the same objects, right? So in a way, we never tested what happens if for some objects you have a point cloud and for some objects you have CAD models, but you don't have the other modality. Can we still do a good job in retrieving information? And so here, again, on the ScanNet dataset, we train with different percentages of data. So for example, for modality image to point cloud and modality image to CAD model, what if we use only 25% of the data in point cloud and 75% in CAD, or 50% point cloud, 50% CAD, or the different percentages that you see here? And 100% would be the one that would mainly perform the best, which is the one that we used. But you see that and I will explain in a second what are the columns, but for a quick look at the numbers, you will see that the performance does not deteriorate a lot, even if we've not seen in all training both point cloud and CAD for the same object. And what we have here is instance matching recall. So we do it on the object level. And same means the recall of whether we are actually able to retrieve objects from the same category. Diff means if we are retrieving an object from a different category. Top 1 means if we are able to retrieve in the top 1 our object that we want, and top 3 within the 3 first choices. And you see that, yes, all our numbers show that even if you had separate point clouds, databases and CAD models, etc., and you do train on this flexible alignment with one modality, you're actually to do extremely well and robust. We also have some experimental results here in terms of visualizations. Here we'll show a success case for us and a failure case for all the other methods. So what we do is we query the floor plan modality that you see down here against a database of point clouds. And we show here what the point cloud should look like, because that is it's only for illustration purposes. We don't use that during querying. And you see here we have point bind, which performs the best across the two prior works. And we also have our instance baseline. And what we see is that they are not able to retrieve this scene within any of the 4 top choices, but ours is actually able to find it at the very first choice. And this is not really a cherry-picked result. What we also see is that among the top choices, it's also able to bring together scenes in the embedding space, scenes that have a temporal aspect, a temporal flare. So these 2 scenes are actually from the 3R scan dataset, the scanned dataset, but they do have a temporal dimension, which means that this was, let's say, captured first, and this one was captured second after certain kind of changes happened in the scene. What that tells us is that it's actually able to bring together in the embedding space scenes that look similar, scenes that have similar geometry, similar semantics, similar appearance. And finally, you see here, the 4th choice is one that actually has a kind of similar layout as the query scene. You see here, there is a couch here. You see the scene layout more or less resembles this one. So it actually is able to pick certain aspects from our training to identify this cross-modal behavior. Now, what you might be thinking is, okay, you're telling me about cross-modal scene retrieval, and you are comparing against an instance baseline and point bind, which is also an instances. How do we exactly do it, since they are all trained on the object level? And I want to clarify that our way to make this comparison fair is that we are averaging the results over the modalities, and then being able to use that average feature vector in order to perform the retrieval on the scene level. So essentially, we're going to take, they do require instance segmentation versus ours does not. And so we're going to take each of those instances that we have from ground truth segmentation in this particular point. We're going to pass them to, say, from point bind. We're going to get an output vector for each instance. And then per modality, we're going to average it. So here, when we are querying the floor plan, the point cloud, we're going to take each of those point clouds, pass it to the point cloud encoder of point bind, get the average feature, look at the features for each instance and average them out. And we do the same for our instance baseline in order to be, to compare a more instance-based method towards our scene level method. Because as I said, there are no methods, at least to our knowledge, that are able to perform scene retrieval in a cross-modal setting. But of course, we are not perfect. And here is a failure example. And we see, again, the query modality is a floor plan. And we go on to retrieve from a point cloud or a database of point clouds the scene. This is what it should look like. You see that actually no method is able to retrieve this scene. But we are able to retrieve mainly offices, which is a good sign. We're not retrieving toilets or dining rooms or something else like the other methods sometimes do. Also, what you see over here is the same scene, but in another temporal point. So we are able to essentially retrieve some close to the first, like second choice, the temporal counterpart of that scene. And so we asked, why did we create this method? Why did we want to do cross-modal retrieval? And maybe you all have different ideas about what you would like to do with it. But in our mind, we thought, wouldn't it be great, particularly for cases of design, like building design, room design, interior design, or even video game design or VR, AR settings, if we were able to, let's say, as a designer, say, oh, I like this image of this building. Do I have anything close in, let's say, my portfolio of things that look similar? Or I like this object in this text kind of format. Can I find something in my database? Or I have this 2D floor plan. Can I find something, an image that looks like it so I can get inspiration? More importantly, for the VR AR setting, what we have in mind to do in the future is that we will take, let's say, this virtual CAD scene that someone has created. We can look at a scene database and find the point cloud that matches closest to it, let's say, for all our point clouds of scenes that we have in, let's say, this building, right? And then we're going to find the one with crossover that is the closest. And let's say it would be this conference room, which looks nothing like the meeting room over there, but close enough. And then on that, we found what is the scene that is the closest, which means if we have created a virtual scene in a CAD setting for our VR experience, we now found the closest room that we can actually deploy it in. And if we do that, then why not also retrieve CAD models that look the closest to the ones we have in our physical space? And why do we do that? Because if we are able to do, we can actually use any space as a physical space as an anchor for a VR space that doesn't require us to have a boundary specification when you're in VR or an empty big space for you to perform whatever game you want. You could actually start interacting and sitting on things while sitting on a virtual chair in the VR setting. And we hope to do that. You see here an application of that. The alignment that we did with the objects is in a brute force manner. So this is about crossover, and we are already extending it to include more data sets and before way more tasks, such as scene understanding, etc. And you will see hopefully that soon coming out. And we aspire to create crossover more like, I will say the buzzword, kind of foundation model for crossover scene understanding, it's a cross-modal scene understanding, but we'll see how far we can come with that. In addition to crossover, which will be presented as a highlight poster by Cheyenne this Friday, but also tomorrow at the Open Sun workshop, we also have WildGS Slam, which if you get out right now and go upstairs to X Hall D, sorry, you will see it. It's being presented in a workshop, but also it will be presented on Saturday and Sunday as a demo. And we also have an AI art entry this year about an AR community art project. If you want, please stop by to contribute to it. We want to make it afterwards public and see how all of you contributed in making a canvas all together. And visit us during the main conference days, particularly if you come during the guided tours, we'll definitely be there to help you out, interact with it. That's it. Thank you very much.
Thanks for the great talk. Any question from the audience? Yeah, please.
Thank you for the great talk. I had a question where the crossover gave non-aligned results. So do you credit that to noisy data, or is it about feeding in more object level information into this training regime?
Yeah, if you take a look at our paper and you look at our results, you'll see that there is still a lot of way to go to make it really accurate. Like our recall is not always perfect. It can be even down to 30% or something like that, which means there's a lot of room for improvement there. We do think that data plays a very important role, so that's why we're trying to scale it up. But also, we're combining many data. You introduce also different noise patterns, different sensor patterns, right? So potentially with all that, it can become more robust. But I do think that thinking also of a better way to do these unified dimensionality encoders where they remove the dependence on semantics could actually bring a better alignment and creation of a unified embedding space. So if anybody has ideas, let me know. I'm happy to chat more.
Thank you.
Please.
Thank you very much for a very nice talk. Actually, an hour ago, I have been to a workshop on fundamental models of medical AI, and they were mentioning multiple modalities for medical AI, and they also have one bounding modality, but in their case, it was text. So I'm interested if you have also considered text as a bounding modality, or if the image was just a only choice.
So that is a very good point. So there are two answers I can give to that. Well, first of all, we didn't try it. However, most of the data sets we have do mainly rely on having images and point clouds that is fairly more easy to find than finding many data sets that do include text. However, even if we had those, at least for the text we are using, which is mainly about relationships between objects, I do not think that only text would work extremely well. In addition to that, even if it was describing the scene in more details, still a text as a grounding modality cannot capture aspects of patterns, of textures, of things that are related to how scene looks like. How well can you describe this floor, like a rug pattern, right? You always not be able to capture it as well as an image would. Like an image is 1,000 words after all. So I do believe that even if we had all the data text in the world describing things in very much detail, scene retrieval will still work better if you had an image modality as a grounding level. Yeah.
Actually, I really agrees with you, and I thought that it will be similar for medical AI, but in their case, it is not.
Right, but I can understand why in that domain that would not be the case.
Thank you very much.
You're welcome.
Maybe actually in a follow-up, I didn't see a reason, first of all, thank you for the talk, but I didn't see a reason for even choosing a binding modality, like fundamental reason to even have a binding modality. What do you think about that? Like, why do we even need to define which modality we want to align everything on? Can't we just don't choose it and still achieve the same goal?
Right. We tried it, Shagan, we tried it and it didn't work very well, right? Yeah.
We need a binding modality for since image in the Windows understanding data sets, image is the most readily available modality. We don't need a binding modality per se. You can also choose any other modality to align to, or you can actually, for one data set, you align to images, for the next data set, you align to point clouds. You can also just do that. But for the best performance, we found that images aligning to one binding modality gives us the best performance.
Yeah. And we tried mainly images because the encoders, pre-trained encoders, since we go from instance to scene, were actually the strongest that we have right now.
Yeah, I was just thinking theoretically you could say every
Yes.
time it's a new question,
Absolutely.
and you just make sure everything is aligned, and you don't say overall we align to images, but we align whatever the current input is with each other.
Correct. And I think actually ImageBind does that, if I'm not mistaken. But in our case, because of the data we have in the 3D domain, it did work better for the, yeah.
Okay, so if there's no further question, let's thank Jürgen.